Hello, everyone. Welcome to the webinar on how to get started with your AI journey using a Raspberry Pi. So we'll start with a brief overview of Digirum's Pi SDK and AI Hub, and then we'll directly jump into some code examples that involve face detection models using Raspberry Pi with and without an AI accelerator. A brief intro about myself. My name is Shashi Chilapagari. I am the co-founder and CTO at Digirum. And let me get started with a brief overview of a couple of our products. So at Digirum, we have been working to simplify the development and deployment of AI applications at the edge. And to make this process easy, we developed two products. One which we call the Digirum AI Hub. What the AI Hub does is it provides a platform to kickstart the development of AI applications without the end users having to invest any time, money, or resources on bringing up the hardware. As you know, bringing up AI hardware, especially edge AI accelerators, can consume a lot of time, money, and engineering resources. Digirum AI Hub provides access to multiple hardware options in the cloud so that you don't have to spend any time on hardware bring up, but directly start with application development. The hub also provides hundreds of production ready, high quality ML models. In a moment, I'll show you the vast public zoo that we have targeting different hardware options that people can immediately start with. But eventually, when they go from development to deployment, everybody would like to bring in their own models. So the hub also provides a compiler in the cloud that allows developers to reliably go from a training checkpoint to a deployed model in a single click. And in future, we plan to add other optional features to the AI hub, such as collecting and labeling data, training the models, and improving the models once they have been deployed, all on the same platform. So the AI hub is free for everybody to sign up. After the brief introduction, I will show you the page where you can sign up, and if you're interested, you can even follow the demo as we do it. The second component that we have developed is what we call the Digirum Pi SDK. It's a software stack for building edge AI applications. And a unique feature of this software is that it is a single software stack that works with multiple hardware options. So Digitum Pi SDK uses a runtime plugin mechanism that allows it to work with various underlying hardware options. For example, using the N2X runtime, it works with Digirum's own hardware accelerator called Orca. Using OpenVINO runtime, it works with Intel CPUs, GPUs, and the latest NPUs. With TensorRT, it works with NVIDIA devices. With TensorFlow Lite, it works with CPUs, Coral Edge TPUs from Google, and a bunch of other new SoCs that have inbuilt NPUs in them. ONNX runtime for generic CPUs. So what this does is end users do not have to spend time in understanding the minute low-level details of the individual hardware and runtime. But using PySDK, they can just focus on the business logic and develop a hardware agnostic software. The inference API is extremely simple. We'll show you in the demo how a single line performs the entire prediction pipeline of decoding the input, resizing it to the size expected by the ML model, pre-processing it, running the inference, and running the post-processing as well. And since there are a variety of model types, for example, classification models, detection models, segmentation models, and so on, the entire PySDK is designed such that people don't have to write any more boilerplate code to visualize outputs. That means for classification models, you will see the labels printed out. For detection models, you will see the boxes. For segmentation model, you will see the masks. For the key point models, you will see the key points drawn. PySDK also has a lot of advanced features that allow you to take full advantage of the underlying hardware. So, for example, to run on video streams, we have a very efficient asynchronous method that allows you to do batch prediction. Easy to add features like tracking, slicing that would allow running very high input resolution images, and compound models, a topic that we are going to cover in detail during this webinar. And the entire PySDK stack has been designed in such a way that you can develop in the cloud. So you can start with Digirum AI Hub, where you don't have to set up any hardware. And once you develop your application, test it, you can deploy the same code at the edge on the hardware of your choice. Today, we already support a bunch of hardware options. As I mentioned, our own Orca, Intel CPUs, GPUs, NPUs, GPUs, and Orin and Jetson type of devices from NVIDIA, NXP IMX 8 and 9 series, AMD CPUs and their latest NPUs, Raspberry Pi, which is going to be the focus of our webinar today, HTPUs from Google, and chips from Rockchip, the 3588, 3566, 3568 that have inbuilt NPUs. We have plans to add other hardware as well. Initial support is now already available for some of the TI-based SoCs, and in future, other SoCs from Qualcomm, Renesas, STMicro, as their software stack and dev kits become available, we'll start adding them. And other edge AI accelerators will also be added on demand. As we know, today edge AI is a very crowded market with a lot of options. And people have to spend a lot of time in bringing up each of these individual hardware because everything comes with its own software. At Digirum, we are trying to streamline this process by making sure that the end user needs to learn only one software option. The benefits of such a stack are obvious because the software is very intuitive and has ready to use models. You can kickstart development very quickly. You can develop in the cloud, deploy at the edge, and you don't have to get locked to one hardware because the software is hardware agnostic. The same software works with multiple options, which also gives you the option to add extra AI compute with the same software. You can start off with an SoC that has an inbuilt NPU. And when you run out of the compute capacity and want to add more AI applications, you can add an accelerator with the same software. And finally, the whole toolchain allows you to port your own models using the compiler toolchain, which means that you can bring in your own models. So that's a brief intro to our AI Hub as well as our PySDK. For those of you interested, you can sign up for the AI Hub, hub.digirum.com, and you can sign up for free. All the tools inside model, public models, everything is free for development purpose. And once you sign in, you will get immediate access to our large public model. So as you can see here, today our public model zoo already contains more than 1,100 models targeting different devices. So we have the N2X runtime working on our Orca, OpenVINO CPU, GPU, NPU, different types of Arcane and Rock chips, TensorRT, TF Lite using Edge TPU, TF Lite using CPU, TF Lite using ARM-NN, a lot of models um, of different types as well. So for example, a lot of classification models to do image classification, a bunch of YOLO V8 models for doing object detection, specifically targeting, let's say, COCO type of models for general object detection, but specific models such as face detection, hand detection, car, license plate, and a few others, some of which we will see in the demo. And of course, things like post detection and segmentation. A key feature of the AI Hub is that without installing any software, people can directly run inference in the browser. So let's say I look for YOLO V8N models. So you can drag and drop an image and run inference in the browser itself. This gives you an idea of the type of models, its accuracy, and not only that, it also gives you an idea of what the frames per second for this model on this hardware would be if it runs locally. So here it shows that YOLO V8N that has been trained for face detection on a 640 by 640 input image will run around more than 100 frames per second if used on Orca. So browser itself allows people to run different models and check the type of models that are supported, also give them an idea of what performance to expect from these models. And once you have decided that the hub is the right tool and PySDK is the right thing to start your AI applications, you can install locally and get started with our hub in under 1 minute. So we'll now start looking at some demos of the code, how you can start with the PySDK, and I will explain how you can run inference on images, how you can run inference on video streams, and how you can run inference on multiple models with very simple code. We'll start with a very simple example where the inference is running in the cloud. So this is, for most people, the fastest way to get started with our PySDK. No hardware setup needed. You can just install on your PySDK on your laptop. And then once you register for the AI Hub, you can generate a token to access our resources and start running your inferences. So the inference API is very simple. As you can see, the first line is what we call the load model. So the load model function takes 4 parameters: a model name. So throughout the demo, we will stick to the YOLO V8N based face detection model that we have trained and compiled for different hardware options. So for the CPU, For our own Orca, for Edge TPU, we'll see different flavors of this model at different sizes and so on. Then you specify where the inference should run. That's specified by the inference host address. That's at cloud. And you specify where the model is located at. It's in the Digitum public zoo, and you provide your token. Once you load the model, you can pass an input image to it. So the input can be passed to an image. It can be a URL. It can be a pill image object. It can be a NumPy array. So different types of input are supported by the forward function of the model. So once you run model of the input, you will get an inference result. And the inference result has the numerical results that you can print out. So since this is an object detection model, it detected 3 different objects. So the inference results have 3 entries, and each entry has a bounding box, a category ID, and a label, and the confidence. So here you have 3 human faces detected by the face detection model. And once you have the text results, we also provide a simple tool to visualize the output. So this is one of the key features of PySDK is that to visualize the output, you don't have to write any more boilerplate code. If you just say Digitum, also PySDK, along with PySDK, we have another package called Digitum Tools that has all these conveniences. We provide a display function in which you can just say show image of the inference result. It will show you the original image with the AI model results overlaid on the image. And of course, if you you can provide a lot of other options, such as showing the labels, choosing different colors, and so on. Some of those options we will see in the next parts of the demo. So this is basically getting started in the cloud. Very easy, and people can get started in under 5 minutes. You can programmatically look at all the models that are in our public zoo. You will see a large number of models reported. So I'm not going to go over all of them, but you can see a lot of flavors just by looking at the list. So we have some clip models from OpenAI that are used for general embeddings. We have efficient net, efficient debt type of models for classification and detection. We have MobileNet V1, V2, the standard models for classification, the famous ResNet. The latest batch of YOLO models, the YOLO 11 series. And we have YOLO V5, V8, different flavors of the V5 series of models, different flavors of the V8, all targeted towards different use cases, as you can see. Person detection, personal protective equipment detection, wider face, key points, car, segmentation, face, fruits, age, gender. So a lot of models for a lot of use cases that allow people to get started immediately. So once you are comfortable with inference running in the cloud, you can switch to local inference. So local inference is when you have the hardware locally, but we actually can run on any PC because every PC has a CPU. If you look at Digitum sysinfo, you will see that on this laptop, we have the TF Lite CPU. So this is a 4-core device. So you can use all TF Lite models using the CPU as the device. So Essentially the same model, YOLO V8N ReLU 6 phase that was working in the cloud can now work locally. And since it is working locally, you don't even need the token. So we have made our public model zoo truly public, which means that to actually get the model and run it locally, you don't need to have a token. Again, you can see same results as you run in the cloud. On the same image, you can see the three faces detected. And the only thing that we changed in the code was this line. So inference host address went from @cloud to @local. So this is the second mode of inference supported by PySDK. So the first mode is a cloud inference. The second is local. We also support what we call an AI server inference. So AI server inference allows you to run an AI server that serves AI models on one machine and have different clients that are running different applications connect to this central server. And the central server can actually be on the same machine as you run the application, in which case we call it the local host. Otherwise, you basically provide the IP address or kind of the name of the server. So here we are now switching from local inference to AI server inference. I will go into a little bit more detail of what this machine is. But again, no surprises here. It's the same type of, it's the same model running on the same image. Again, since you are not utilizing any of our AI hub resources, no token is needed in this scenario. So all three use cases, running inference in the cloud, running inference locally on the machine where both the client application is directly talking to the hardware, and third case where the AI server is running on a different machine and you are communicating through server client protocol. Now let's look at this machine DGSRV57. So this DGSRV57 actually is something that I have on my desk. So it's a device that has a TF Lite CPU, N2X CPU. It also has a TF Lite Edge TPU. We'll come to that in a bit. Let me actually show the machines that I have here. So this is a Raspberry Pi 5 connected to an Edge TPU, and another Raspberry Pi 5. So this is DGSRV58, but this time it has our Orca on it attached through a Raspberry Pi hat. So throughout the rest of the demo, we will be using these two machines to see how we can run different models. So far we have seen very simple type of APIs to run AI on an image. Again, this is something that people would have seen in a lot of other scenarios. Running a model on an image is not too difficult, but now we'll go to something that allows us to run AI on a video stream. So we have the YOLO V8N ReLU 6 quant model that is running on DGSRV57. So as you can see, it's basically running the face detection model on the Raspberry Pi. Of course, the client application is running on my laptop, but you can get both of them running on the same machine. As you can see, not too fast because Raspberry Pi is still a weak kind of CPU. You can expect about 9 or 10 frames per second for this type of models. Of course, you can get higher performance by compiling the same model at lower resolution. So instead of running the model at 640 by 640, you can compile it for 320 by 320. And since the size is smaller, now you will see the model running much faster. So this is a trade-off that you can do in terms of the speed versus the accuracy. As you compile the model for lower and lower resolution, of course, you will lose on accuracy. But depending on your application, you can decide what the best uh, resolution for your input should be. If you are working with Raspberry Pi attached to it and a camera attached to it and doing some project that involves looking at objects nearby, even 320 by 320 is good enough, as you can see from this demo. We can quickly benchmark the models. So all of these scripts, by the way, are public. So here we show there are different YOLO V8N ReLU 6 models, the float and the quant compiled for different sizes, 320 and 640. So 4 different models, float and quant 320 and 640. And you can see what is the performance that you can expect from each of these models. And we provide this simple benchmarking script that will allow you to see how many frames per second to expect. Takes a few seconds to run all the 4 models, but you can see that the YOLO V8N phase 320 by 320, even the float will give you about 44 frames per second, and the quant will give you about 63 frames per second, compared to the 640 by 640 that gives you about 11 and 12 frames per second. Which means that at this resolution, even baseline Raspberry Pi should be able to support a couple of cameras, or on a single camera, a couple of the models. Of course, typically we have other application code running, and as you add more and more application logic, you might realize that the CPU is being used and you don't have much compute power left for the AI models. So one way is to attach an AI accelerator. So as we mentioned, one of the key features of PySDK is its ability to support multiple hardware with the same software. So now we'll show you how you can basically, if you look at DGSRV57, it not only had the CPU, but it also had the edge TPU. So that means we should be able to run the edge TPU models. As you can see in the code, the only line that changes is the model name. So instead of saying YOLO V8 and ReLU 6 phase quant TF-Lite multi-device, it says TF-Lite Edge TPU. That means this is a model that has been compiled specifically to run on Edge TPU. And now if you run this code, instead of running it on the CPU, it will run on the Edge TPU. And since Edge TPU actually has higher performance, you will now see that the 640 by 640 can actually run at more than 30 frames per second. Here you are seeing 30 frames per second because we are actually limited by the camera speed itself. We can look at another hardware. So this is DGSRV58, which is also a Raspberry Pi. But now instead of having Edge TPU, it has Orca 1. So this is another accelerator. This accelerator is actually developed by Digitum. So again, the same code, instead of saying YOLO V8 and edge TPU, now you will say it is N2X Orca 1. So these lines of code basically show you that to change where you are running the inference, so you just change the address. To change the hardware, you just change the model name. And rest of the code you don't have to touch. Right? So with very simple changes, you can actually uh, run the same code across different hardware options. In fact, when you finally develop such applications, such variables are put into some configuration file, and you can just have a different configuration file for different devices. Again, this is what we consider to be simple use cases. So you have a single model and running single model across different hardware, across different models. Um, Nothing too spectacular. So the power of PySDK comes when we consider multiple models. And this is one scenario that PySDK is very good at, and we'll explain a little bit what is happening here. So let me run the code, and while it comes up, I can explain what's going on. If you look at real life sophisticated edge AI applications, they are never necessarily just a single model. So for example, you have a face detection model, but let's say you are developing an application for retail analytics, uh, in which case you want to do some type of demographic analysis. Right? So you want to get the age, gender, and maybe even see the emotion of the people. So that means you should be able to take the output from the face detection model, send it to a classification model that will tell what the gender is, and then show the results. Right? And the code, I have asked my colleague Alex to join so that people who are looking at the demo don't see that I just changed in the model the output to just say male, so that the model is actually running. So to do such a complex type of pipeline, right? So for example, even in this simple scenario, here we have two people, right? So that means the face detection model gives you two boxes. And now you have to send the two boxes to the classification model, get those results, put them together, and then show them with different colors. As you can see, the male here is shown with green color, female with yellow color, and so on. So how do we achieve this type of simplicity of code? So for this, we have developed what we call a compound model. So a typical use case that involves multiple models is the first model being a detection model. So you detect something, and then after you detect, you classify. So it could be either something like gender, male versus female, or it can be something like a regression model that predicts age, or it can be another classification model such as emotion, or some other things like attributes of the face. Is the person wearing glasses? Is the person wearing earrings? Right? Do they have a beard? What? So different types of face attributes. So all of these again falling under the classification model. So for this, we have designed a tool in the Digitum tools called crop and classify model that takes the first model and the second model and tells you how much to crop it. So basically this code is saying that define me a new model that takes output of the face detection model, crops it by 10% because sometimes the face crop, if you remember from the previous one, is very tight on the face. But for classification model, you might need a larger crop because there can be more details about the gender in a larger crop. You expand the crop by 10% and basically Now it behaves like any other model. So that means you can run the predict stream function. So run predict stream on the video source. So the video source here is one, which is my webcam, but the video source can be an RTSP stream. It can be a video file. It can even be a YouTube video URL. So, and then you just show the inference result. So that's basically how you run two models in series. We can do different example, which is actually a face detection followed by age. So the age estimation is not a classification problem, but more of a regression, but the code doesn't change. Mm, so here you do the same thing. You have a face detection model, you have an age model, and you basically crop and classify. Of course, the age model has a lot more variation than the gender model. But since these are typically used in statistical kind of settings, so retail analytics where you actually don't need to know the exact age. You just need to be able to put them in a bin, whether they are between below 18, 18 to 26, 26 to 40, or larger bins than precisely knowing their age. And finally, a little bit more fun demo where we also have an emotion model. So again, the idea is the same. You have a face detection model, you have an emotion classification model where you provide the output of one model to the other, and it basically shows in real time how the emotions are changing. Of course, the model itself needs a lot of work, as you can see, but if you have extreme emotions, it is pretty good at detecting, such as surprise or very sad, happy. We are seeing a lot of interesting applications for these type of models. One use case is engagement in meetings or classrooms to see how engaged are people in such settings. Um, of course, the age and gender models traditionally used in the retail kind of setting. Anyway, the idea behind the demo is that uh, this is not just for the face age or face gender, but any combination where you have a couple of models, you can easily pipeline them using the compound model that we have. The final part of the demo, I want to show something where we can add a tracker. So as you know, tracking is basically running the model on a video stream only gives you frame by frame info. But if you want to track people, that means have the same information across frames on a video. Again, very useful in different applications such as retail analytics, where you're trying to see how long are people waiting in queues, or how many people, what is the average wait time, how many people are entering the room, leaving the room. In all of these scenarios, just doing a frame by frame analysis is not sufficient. So you need to have some form of tracking attached to it. And in Digitum tools, we provide an easy way to attach a tracker to a model. So again, here we have the face detection model and we have a tracker. So In the object tracker, we say, track human faces, provide some parameters for the thresholds and how much buffer to hold. Different trackers use different metrics. All of this will be available in our uh, documentation page, how to use these type of things. But once you have a tracker, what you do is you attach it to a model. So that means whatever results come out of the model are automatically fed to the tracker, and now you will get assigned a track ID. So previously, if you saw the inference results containing a bounding box, a score, a label, and a category ID, now the inference results will also contain a track ID. So this allows you to basically develop even more sophisticated applications that involve tracking people, tracking objects. It could be vehicles, it could be things moving on a conveyor belt in the industrial automation setting, and a lot of other use case scenarios. This brings us to the conclusion of our demo portion. So there is a Q&A page and also a chat page. If anybody has any questions, they can type. We will post the recording on YouTube and send a follow-up email to the participants with resources, links to different resources. This will also give participants a way to contact us in case they have any questions or any inquiries. We have one question. To what extent do results differ depending on the camera module? Yes, so there are two components here. One is the resolution at which the model is trained. So typically ML models like object detection models are trained at a resolution of 640 by 640, which means that no matter what the resolution of the camera is, what goes into the ML model is a 640 by 640 image. And this can basically cause some performance degradation. So you might have a very high resolution camera, but because you have resized it to a smaller size, you're not able to detect smaller objects. And there are a couple of tricks to overcome this. So you can kind of do what we call tiling or slicing. So do a bigger image into smaller chunks and then run inference on all of the different slices and combine the results. So that's one way to get higher accuracy. Of course, the same thing from different cameras can also give different results, especially if the lighting conditions or noise changes. So that's why it is very important to actually fine tune the model after it has been deployed, so that it is fine tuned to your exact use case. We have another question. Is your software something similar to ONNX? The answer is both yes and no. So ONNX also has a plugin mechanism that allows you to work with different hardware. So they provide a mechanism for you to add your own hardware so that the same ONNX API works on multiple hardware. But what we have done with PySDK is work on one level of abstraction above. So instead of just running the AI inference, lot of application support has been provided to do rest of the pipeline. Uh, so pre-processing, post-processing, things like tracking, ability to run multiple models. Uh, in the next webinar, we will also cover new PySDK and Digirum tools features, such as integration with notifications, event detection, and so on. So you can think that the PySDK is at the application software level that provides a lot more functionality than the simple ONNX runtime.
Looks like we have another question in the chat, Shashi.
Yeah, I'm reading through. Uh, I'm not sure I understand fully. Building a similar model, custom RNN, CNN object detection, leveraging the methods you went through would show more impact than customer built models help the model. Maybe we can follow up Alex with him to understand a little bit more of what the context around is.
Absolutely.
Okay, if there are no more questions, we would like to thank all the attendees for joining. As I mentioned, we will follow up with the recording as well as resources for you to replicate whatever we have shown in the demo today. So we will upload the notebook to GitHub and share the link so that all attendees can essentially run the same demo on